All right, so we see this problem, and we want to kind of go running for the hills and abandon it, but it's really not as bad as we might think. So let's try to draw some pictures and get a better feel for what's going on here. All right, so the first thing we want to do is realize that we've got, we're told that iron and nitric acid will form iron 3 nitrate, water, and nitrogen monoxide. And then you've got this unknown ore that contains iron, and so you want to analyze it. So let's draw a picture of that ore. So here's the ore, and somewhere in that ore we've got iron. All right, some part of that ore has iron in it, and we want to find out how much iron was in that ore. So what we're going to do then is we're going to put that whole sample of ore into nitric acid, and then the iron will react as described in the first sentence there. So the iron will react with the nitric acid, producing. So iron is going to be in the solid state, nitric acid in the aqueous state. The products are iron 3 nitrates. Let's see, 3. So iron's a 3 plus, nitrate's a 1 minus, so we're going to need FeNO3 taken taken 3 times, and that'll be aqueous in the water, since this is all happening in an aqueous environment. We're going to form this NO gas, nitrogen monoxide, and we're going to make some water, and that would be a liquid. Now, the equation is not balanced, so we'd have to do a little bit of balancing here. Let's see, we'd probably want to start with a 1 in front of the iron 3 nitrate, right? In this case, we cannot balance the nitrates together, so we're going to have to do, well, it's going to create a little bit of a problem here for balancing, because you can see that we've got nitrogens and oxygens in the iron 3 nitrate, but we also have nitrogens and oxygens in the NO. And then over on the other side, we've got the HNO3 as the sole kind of place where we're getting the nitrogen and oxygen from. So what I'm thinking we're probably going to do is start by a little bit of a guesstimation here. We know we have to have at least 4 of these, because we need 3 nitrogens just for the iron 3 nitrate, and then we would need at least 1 more nitrogen for this nitrogen monoxide. So let's try that and see how it works out. If not, we can always go back and change the 4 on the nitric acid to a 5, and kind of keep working our way that way. So we would have, how many oxygens have we got here? So we have 12 oxygens on the left. I have 9 oxygens in the iron 3 nitrate, and then 1 more in the nitrogen monoxide. It gives me 10. So I need 2 more oxygens. So if I put a 2 here with the water, that gives me the right number of oxygens. And fortunately, that also gives me the right number of hydrogens. So I have 2 hydrogens on the right and 1 hydrogen on the left. And now I can go and just put the 1 in for the iron to make that balance. All right, so there's my balanced equation. And now what I want to do is analyze that gas that was collected to try and figure out the moles. So we know kind of about the volume of this that was collected. So we have 250.55 milliliters of gas collected. We know the temperature is 22 degrees Celsius. And we know that the gas collected was brought to room pressure of 0.950 atms. The only thing we have to remember is that that's the pressure total. So to get the pressure of just the nitrogen monoxide, we're going to have to subtract out the vapor pressure of the water. So we need to get then, according to the question, we want to go from this information about the nitrogen monoxide to figure out how much iron was produced. So there seems to be a 1-to-1 mole ratio there. So if I can get the number of moles of nitrogen monoxide, then I can get to moles of iron, and then grams of iron. All right, so we're going to have to go consult a table to find out the vapor pressure of water at 22 degrees Celsius. I guess I should back up for just a minute. So this is obviously a gas law stoichiometry problem. So to get the moles of NO, so let's use our formula to kind of guide our work here. We're going to use PV equals nRT. So pressure of the NO, volume of the NO over R and T. So here's where we run into the stumbling block. We don't have the pressure of just the nitrogen monoxide. We got the pressure total. So coming over here then to get the pressure of just the nitrogen monoxide, I'm going to take my pressure total and I'm going to subtract the other gas that's in there, which is the water vapor. So my pressure total, 0.950 atms. My vapor pressure of the water at 22 degrees Celsius is 19.8 millimeters of mercury, so I'm going to have to convert that to atmospheres. And I convert that to atmospheres by dividing the 19.8 by 760 millimeters of mercury, and I end up with 0.026 atmospheres, which then gives me a pressure for just the nitrogen monoxide of 0.924 atmospheres. All right, so now I've got the pressure that I can plug in over here. So 0.924 atmospheres. And my volume, so the nitrogen monoxide is going to occupy the same volume regardless of whether the water vapor is there or not. It's occupying that whole volume. We've accounted for the presence of the water vapor by subtracting it from the vapor pressure, or from the total pressure. So we don't need to change the volume. So it would be 0.25055 liters. So I'm going to put these in the right units so it will work with our value of R. R is 0.08206 liter atmospheres per k-mole. And temperature, remember we need to use Kelvin whenever we use calculations with the temperature. So we're going to have 295 Kelvin. And let's scroll down here and we'll get the number of moles of nitrogen monoxide. And our moles of nitrogen monoxide is going to be 9.56 times 10 to the negative third moles of nitrogen monoxide. And so now we can just do a mole ratio to get to the iron and then the grams of iron. So we would have our 9.56 times 10 to the minus third moles of the nitrogen monoxide. I know from the balanced equation that 1 mole of nitrogen monoxide is produced from 1 mole of the iron. And 1 mole of iron has a mass of 55.8 grams of iron. And we'll make sure we can cancel all these units out. Moles of NO, moles of NO, moles of iron, moles of iron. And then we'll calculate this answer. And we end up with 0.534 grams of iron. So just over half a gram of iron reacted to produce this volume of nitrogen monoxide.